Hi again, everyone. Dr. Tom McNamara back for our course in college algebra. In this video, I would like to continue our work with quadratic expressions and discuss quadratic inequalities. Earlier in the course, we had already discussed absolute value inequalities, and we made use of a chart there as well. So we're going to revisit that idea here. So the basic steps when you're presented with a quadratic inequality is get a zero on one side, solve the related equation, and then go and do the chart. So let's go and look at a couple quick examples here. Okay, so what I want to do is I want to solve this inequality, x squared minus 13x plus 22. I want to figure out where that is less than or equal to 0. All right, so I've already got a 0 on one side, so I'm good to go there. So my first step will be to solve this related equation. You probably guessed what the related equation was. Okay, well, I think I can solve this by factoring. 22, I'm thinking of numbers that multiply together to give me 22. 2 and 11 are candidates. They add together to give me 13, so that's convenient. I think they should both be negative. So x minus 11 and x minus 2. All right. So reason being, this plus tells me that the constant terms here should have the same sign. That tells me they should both be negative. All right, so here's what I'm going to do. On a number line, I'm going to plot those solutions. You've got to put them in numerical order, right? This factor corresponds to a solution of x equals 2. And this factor corresponds to a solution of x equals 11. So my solutions are 11 and 2. Well, on the number line, 2 would be over here to the left of 11. So we're going to use that to break up the real number line into regions. This region represents everything less than 2. We're going to pick a representative test point for that region. I pick 0. Anything less than 2 will work. Okay, over here I'm going to pick 3. This region represents real numbers between 2 and 11. 3 is in there, okay? Once again, anything in that region will work. You want to pick 4, you can go ahead and pick 4. Doesn't matter. Something bigger than 11. Okay, I pick 12. Okay, now I'm looking at plugging those test points into this expression and thinking about it in relation to this inequality over here. Okay, if I plug in 0, this term is negative. Right? 0 minus 11 is minus 11. So I get a negative when I plug that test point in here. When I plug that test point in here, I also get a negative. Negative times negative is a positive. Okay? Take this point, x equals 3. You plug it in here, 3 minus 2 is 1, it's positive. 3 minus 11 is negative 8, that's negative. So you have a negative times a positive, the resulting product would be negative. And you can do a computation there. If you plug in 12, you'll get positive times positive, so the resulting product would be positive. So the question now becomes, which of these regions is part of my solution set? Okay, well, I was looking for values of x that make this expression, x squared minus 13x plus 22, I'm looking for x values that make that expression less than or equal to 0. Well, that means this is out, because if I plug in stuff from this region, I will get something bigger than 0. I'll get something positive. I don't want that. I want it to be less than or equal to 0. This region works, this one does not. So my solution set is x values between 2 and 11 inclusive. If you like inequality notation, 2 less than or equal to x, less than or equal to 11. This is the corresponding interval notation for that solution set. All right, let's do another example. So, let's try this inequality. Let's do x squared plus x greater than 6. All right, so we're going to find the set of all x values that make this a true statement. Okay, so if that inequality is true, then this one is also true. Okay, so first step, you'll remember, was get a 0 on one side. Subtract 6 from both sides, and we've got that. Now we're focusing on the related equation. Okay. Well, I'm just going to kind of think of the equation in my head here. It's not too hard to see that this expression factors. Okay, you're thinking of numbers that multiply together to give you -6, so they've got to have opposite signs. So I guess your choices are 1 and 6 or 2 and 3. You could have a combination of different signs there. No, I had it wrong. +3 and -2 are the ones that do the job, because I want a +1 in the middle, right? First times first is x squared. -2x plus 3x gives me my +1x. And then last times last gives me -6. Okay, so based on having the factoring, I know the solutions to the related equation. Set each of the factors equal to 0 and solve those linear equations. So if x plus 3 is equal to 0, that must mean x equals -3. If x minus 2 equals 0, that must mean x equals 2. So once again, we are picking test points. Those are my choices: -4, 0, and 3. Like I said, you can pick any test point that you like, as long as it's in the region. So for this region, you just have to pick something bigger than 2. You can pick 3, you can pick 7, you can pick 4,000, whatever, as long as it's bigger than 2. Okay, what do? We take those and we plug those into our polynomial expression here. Looking at the result. Really, I care about the sign. I don't care so much about the numerical value. So you'll notice I don't actually do a computation here, right? If I take x equals 3 and plug it in here, yeah, I get 6, but the important thing for us is that I get a positive value. If I plug that x value in here, 3 minus 2 is 1. What matters is that it's positive. So if I plug in 3, this factor is positive, this factor is positive. The product of two positive numbers is positive. If I plug in 0, this factor is positive, this factor is negative. I have one of each in the product, so the result is negative. Here, if I plug in -4, this factor is negative, so is this one. I have two negatives multiplied together. The product of two negatives is a positive. Which regions are part of our solution set? These two on the outside, because in this case, we want the set of x values that make this product greater than 0. In other words, these guys. This region here in the middle is going to make it less than 0, so that's out. Okay, so my solution set, if I use interval notation, it would look like this. I can take x values less than -3, so negative infinity to -3, together with x values greater than 2. Okay, you might be asking, how come I'm using the parentheses here, whereas in the last example we did, I used brackets? Well, go back and check. You'll see in the last example we had less than or equal to 0. This is strictly greater than 0. So these guys are values that make this expression equal to 0. We don't want them in the solution set. We'll do a quick connection with graphing. If I were to draw a very quick plot of x squared plus x minus 6, okay, well, I know where that expression is 0. It's 0 at x equals -3, and it's 0 at x equals 2. So that's telling me the x-intercepts of my function's graph. Okay, those are my x-intercepts. So the graph is a U-shape, looking basically like that, without getting too picky about anything. All right, so where is this thing above the x-axis? Because that's what we want, greater than 0. Okay, well, this thing is above the x-axis for this region right here, for the x values that are less than -3, and for this region over here, for the x values that are greater than 2. Between -3 and 2, the graph is below the x-axis because the expression is giving us negative numbers for those x values. Okay, so everything we do is always kind of connected to the other stuff we're doing. If we're doing something algebraically, it's connected to something we can see graphically. If we figure out something graphically, it's connected to something we can do algebraically. So always look for those links between the topics. Okay, so the key things for solving quadratic inequalities are: get a 0 on one side, solve the related equation, typically by factoring. If we can't factor it, we'll have to fall back on the quadratic formula, and then make this chart. Okay, for those of you that go on to take calculus, this chart is very useful. You'll see this a lot in something called the first derivative test when you take your calculus.